Hello. Now we will calculate the capacitance of a capacitor which is partially filled by the dielectric. But this time the dielectric, the cross-section area as well as the width of the dielectric is not same compared to the capacitor. So its width is d by 2, which is half of the width of the capacitor. Its cross-section area is a by 2, which is again half of the width, this cross-section area of the capacitor. These values we have taken so that the calculation wise it should be easy. Main thing is concept. Okay. So in this case we want to calculate the effective capacitance. So one thing we have to understand, this case or the case where this same dielectric is placed anywhere in the same orientation is same. So if I'm going to move this dielectric either downward or perpendicular to cross-section area, the effective capacitance of this capacitor will not change. But without changing the orientation, meaning I have to move it, not rotate it. We should not be rotating it. Okay. So if we do that, there is no problem. The capacitance will remain same. So if an examiner will place this dielectric, let's say in between, to calculate the effective capacitance from the in between, we will bring the dielectric either to the topmost corner or to the bottommost corner. Okay. Now, we also learned that in the previous lectures we learned that any dielectric, we can cut the dielectrics perpendicular to the cross-section area as well as parallel to the cross-section area as well as perpendicular to the cross-section area. It's up to us. The thing is, if we are cutting the dielectric, we are cutting the capacitor parallel to the cross-section area, the portions we have to reattach them in series. And if we are cutting the capacitor perpendicular to cross-section area, we have to join the portions parallel to one another. So in this case, what we will do, we will cut it twice. So first, we will cut the dielectric perpendicular to cross-section area. As you can see, a half cross-section area is there, so we will cut the dielectric exactly half in between. And the upper portion, we will cut parallel to the cross-section area as well. So after cutting this system, now we are having three systems, C1, C2 and C3 we are calling them. And now we have to join them. So between these two systems, we cut the capacitor parallel to the cross-section area. So when we cut the capacitor parallel to the cross-section area, we have to join them in series. So these two will be connected in series. This one and this one. And the first one is completely filled with the dielectric of dielectric constant 2. This is air. The cross-section area is a by 2 and the width is d by 2. Here also it is a by 2 and d by 2. And this one, actually the third one, in the beginning we cut it perpendicular to cross-section area. So these two will be connected with the third one in parallel. The third one will be having the same area of the previous two, like a by 2, but the width of the third one will be d. There is also air. So effective capacitance of this system will be similar to the effective capacitance of this system. Now let's write the formula. The formula to calculate capacitance is A epsilon upon D, where A is cross-section area of the capacitor, D is width between the plates, and epsilon is permittivity inside the capacitor. And this epsilon basically it might be the air or it might be the dielectric as well. By using the formula, first we will calculate the C1. The C1 is having the a by 2 cross-section area, d by 2 width, and inside it there is a dielectric of dielectric constant 2. So we'll write the value. A by 2 epsilon naught multiplied with k, and the value of k is 2, divided by width, which is d by 2. So this C1 will become 2 times of A epsilon naught upon D. This is equation 1. Now C2. The cross-section area is a by 2. Inside is air, so this epsilon, in place of epsilon, we'll write epsilon naught, which is the permittivity of air, divided by d by 2. So that value becomes a epsilon naught upon d. This is equation 2. And let's go for C3. C3 will become cross-section area, again a by 2. Inside it is air, so epsilon naught divided by d. So C3 will become a epsilon naught upon 2d. Okay. So we have got the values of C1, C2 and C3. Now first we'll calculate for C1 and C2. Since you can see the C1 and C2, they are connected in series. So we'll use a series formula. So we'll use series formula for C1 and C2. So 1 upon C effective between C1 and C2 will be 1 upon C1 plus 1 upon C2. This is our series formula. So we'll write the value of 1 upon C1, which will become D by 2A epsilon naught. Then we'll write the value of C2 or 1 upon C2, that will be D upon A epsilon naught. And the value here will become 3D upon 2A epsilon naught. This is 1 upon C effective. So C effective will be 2A epsilon naught upon 3D. This is the effective capacitance of these two capacitors. Now, these two capacitors are joined with the third one. So we'll use this is a series combination, series formula. Now we'll use the parallel formula. Parallel formula between C effective and C3. This is a C effective. And the parallel formula is C effective dash is equals to C3 plus C effective. Capacitance of 1 plus 2 and the capacitance of third. Okay, so this will be, we'll write the values 2, 3, sorry, it is 3. So this is the C effective, 1 plus 2, plus the third one, which is A epsilon naught upon 2D. So this value you will see, this will become 4A epsilon naught plus 3A epsilon naught divided by 6D. If you add these, the effective value of the combined system C effective dash will become 7A epsilon naught divided by 6D. This is the effective capacitance of this combined system. So in this lecture we learn two things actually. The first thing was the system where I'm placing this dielectric at one of the corner. This system or when we are placing the dielectric in between somewhere, they all are same. Orientation has to be same. If the orientation is same, this dielectric, you can move this dielectric anywhere inside the capacitor, not outside. You don't have to take this outside. Inside, anywhere you can move it. There is no harm in that. So when you are moving a dielectric perpendicular to cross-section area or parallel to the cross-section area without changing the orientation, C effective don't change. And the second thing is, earlier we learned that we can cut the dielectric. We were cutting the dielectric either parallel to the cross-section area or perpendicular to cross-section area.